Imagine standing on the edge of the world, where fire meets water in an eternal dance of creation and destruction. 4 billion years ago, there were no oceans. No blue horizon stretching endlessly before you. No waves caressing distant shores. The earth was a hellish furnace, glowing red beneath a poisonous sky. And yet, in that inferno, the greatest transformation in our planet's history was about to begin. What could possibly turn a molten wasteland into the cradle of life itself? The answer lies not in gentle rains or celestial gifts, but in violence. Unimaginable violence from the planet's core, expressed through countless volcanic eruptions that would, paradoxically, fill the empty basins with the very essence of life: water. This is not a story of tranquil beginnings. This is the story of how fury created beauty. How destruction gave birth to creation. How the same forces that can obliterate entire civilizations once sculpted the oceans that now cover 70% of our world. The question that haunts geologists, that drives their research into the deepest trenches and highest volcanic peaks, is deceptively simple. Where did all that water come from? For decades, we believed it fell from the heavens, delivered by icy comets in a celestial bombardment. But the evidence carved into ancient rocks tells a different tale. A tale written in crystals formed under crushing pressure, in gas bubbles trapped for eons in the chemical signatures of minerals that could only exist in one place, deep within the Earth itself. The planet was hiding an ocean. Not on its surface, but locked away in its mantle. That vast region of superheated rock lying between the thin crust we stand upon and the molten iron core far below. And the only way to release that ocean, to bring it from the depths to the surface, was through volcanic action on a scale we can scarcely imagine today. Picture the young Earth still cooling from its violent birth. Beneath the hardening crust, convection currents churn through partially molten rock, creating cells of rising heat and descending cold that would, over millions of years, fracture the surface into plates. Were these plates pulled apart, magma welled up. And with that magma came something else: water vapor, carbon dioxide, and other volatile compounds, trapped for billions of years in the crystal structures of deep minerals. Each eruption was an exhalation. Each volcanic vent, a release valve for the planet's imprisoned ocean. And there were not dozens, not hundreds, but millions upon millions of these vents erupting continuously over hundreds of millions of years, gradually filling the atmosphere with steam until finally the planet cooled enough for that steam to condense. Then came the rains. Rains that lasted not for days or weeks, but for millennia. Rains that fell upon a world still punctuated by volcanic fire, creating vast clouds of steam where drops met molten rock. Slowly, inexorably, the low places filled. Basins became seas. Seas became oceans. And the volcanic fury that created them did not cease, but merely changed its theater of operation, moving beneath the waves to continue its work of creation. Today, we stand at the edge of those same oceans, often forgetting that beneath the peaceful blue surface lies a volcanic engine still running, still creating, still destroying. The mid-ocean ridges, stretching for over 60,000 kilometers across the ocean floors, mark the places where that ancient process continues even now. How do we know this story? How can we be certain that volcanoes, not comets, gave us our oceans? Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. Have you ever wondered where all the water in our oceans came from? For a long time, we thought it arrived late to the party, delivered by icy comets from outer space. But the real story is far more dramatic, and the clues are hidden in the oldest rocks on Earth. Let's travel to a remote place in Western Australia called Jack Hills. Here, geologists found tiny crystals, no bigger than a grain of sand. These are zircons, microscopic time capsules over 4 billion years old. When scientists analyzed them, they found something that completely rewrote our planet's early history. These crystals had chemical signatures proving they formed in the presence of water that had been cycled through volcanoes. This means oceans began forming almost as soon as Earth's crust solidified, far earlier than we ever imagined. But how did volcanoes create the oceans? The proof isn't just in ancient rocks. It's happening right now, deep beneath the waves. Robotic submarines have explored mid-ocean ridges, underwater mountain ranges where new crust is born. They found incredible hydrothermal vents known as black smokers spewing superheated, mineral-rich water into the freezing depths. Here's how it works. Seawater seeps deep into the ocean crust, where it gets heated by magma. This superheated water dissolves minerals from the rock before erupting back out of the seafloor, through these chimney-like vents. It's so hot it could melt lead, but the immense pressure of the deep ocean stops it from boiling. As this hot fluid hits the cold seawater, minerals crash out, creating the smoke and building the chimneys taller. In this process, new water, locked inside the rock and magma, is released into the ocean. It's the same process that started forming our oceans billions of years ago. Scientists estimate that the entire volume of Earth's ocean cycles through these vent systems every 10 million years. In the grand scheme of things, that's just a blink of an eye. Over Earth's long history, our ocean water has been recycled and renewed through volcanic activity at least 400 times. So if volcanoes are constantly adding water, why aren't the oceans getting bigger and bigger? The answer lies in a beautiful planetary balancing act. While new water is being created at mid-ocean ridges, old water is being removed somewhere else. This happens at subduction zones like the Mariana Trench, the deepest place on Earth. Here, one tectonic plate slides beneath another, dragging down huge amounts of ocean water trapped in sediments and minerals. As this water goes deeper into the hot mantle, it's squeezed out of the rock. This released water then fuels the explosive volcanoes you see in places like the Pacific Ring of Fire. It's a gigantic, slow-motion water cycle. Water from the surface is pulled into the Earth's interior, and then erupted back out through volcanoes. This incredible cycle, driven by the heat of our planet's core, has maintained the balance of our oceans for billions of years. It's a powerful reminder that the Earth is a living, breathing system, constantly creating and recycling the very water that makes life possible. The evidence is all around us, from the tiniest crystals to the deepest trenches, telling a story more amazing than we could have ever guessed. Thanks for watching. If you found this journey into our planet's past as fascinating as I did, don't forget to like and subscribe for more deep dives into the wonders of our world. Our planet is a dynamic world, constantly in motion. Continents drift, oceans expand, and mountains rise and fall over geological time. For scientists, understanding these colossal forces is a grand challenge. But what if there was a place where you could see these processes happening right before your eyes? A place where the Earth's inner workings are laid bare. That place is Iceland. Nestled in the North Atlantic, Iceland is more than just a land of fire and ice. It's a living, breathing laboratory for geology. Here, the story of how our oceans are born is written in rock, steam, and lava. This island nation sits astride one of the most significant geological features on Earth, the Mid-Atlantic Ridge. Imagine a gigantic seam running down the center of the Atlantic Ocean. This is the Mid-Atlantic Ridge, a massive underwater mountain range that stretches for thousands of kilometers. It marks the boundary where two of the Earth's tectonic plates, the North American and the Eurasian plates, are pulling apart. As they separate, molten rock, or magma, from deep within the Earth's mantle rises to fill the gap. This process, known as seafloor spreading, is constantly creating new oceanic crust. Most of this incredible activity happens deep beneath the waves, hidden from our view. But Iceland is unique. It's one of the few places on the entire planet where this mid-ocean ridge emerges above sea level. This gives scientists an unparalleled opportunity to walk on, study, and directly observe the creation of new land. The very existence of Iceland is a testament to this powerful geological dance. The island was formed by a relentless series of volcanic eruptions over millions of years, as magma pushed its way to the surface along the rift. This is why Iceland is one of the most volcanically active regions in the world, with over 30 active volcanic systems. When you travel across Iceland, you're literally walking on the newest crust on our planet. The evidence is everywhere. At Lyngvellir National Park, a UNESCO World Heritage Site, you can stand in the Rift Valley itself. On one side is the North American Plate, and on the other, the Eurasian Plate. The ground is scarred with deep fissures and cracks called JJR in Icelandic, tangible proof that the two continents are drifting apart at a rate of about 2 centimeters per year. It's a surreal experience to physically stand between two continents. But it's not just about the solid ground. Iceland's volcanic activity also plays a crucial role in studying the Earth's atmosphere. When volcanoes erupt, they don't just spew out lava. They release massive amounts of gases that were trapped deep within the Earth. These gases, including water vapor, carbon dioxide, and sulfur dioxide, are the very same elements that helped form our planet's early atmosphere billions of years ago. By sampling these volcanic gases directly at the source, scientists can get a snapshot of the chemical composition of the Earth's mantle. It's like taking a sample from the planet's primordial soup. This research helps us understand not only how our atmosphere was formed, but also how it continues to evolve. These natural emissions provide a baseline for studying the impact of human activities on our climate today. Furthermore, Iceland's unique geothermal features, like geysers and hot springs, are direct results of this interaction between magma and water. Groundwater seeps deep into the Earth's crust, where it's superheated by the underlying magma. This hot water then rises back to the surface, creating spectacular displays like the famous Strokr geyser, which erupts every few minutes, shooting boiling water high into the air. These geothermal areas are not just tourist attractions. They are windows into the plumbing system of an active volcanic zone. Studying these systems helps us understand hydrothermal vents on the ocean floor, which are teeming with unique life forms that thrive in extreme conditions, completely independent of sunlight. The chemistry of Iceland's hot springs provides clues about the potential for life to exist in similar environments elsewhere in the solar system, like on Jupiter's moon Europa or Saturn's moon Enceladus. The constant creation of new crust in Iceland also gives geologists a perfect place to study the properties of young volcanic rock. As lava cools, it solidifies into basalt. The magnetic minerals within the molten rock align themselves with the Earth's magnetic field at that moment in time. Since the Earth's magnetic field has flipped its polarity many times throughout history, the rocks on either side of the mid-Atlantic ridge show a symmetrical pattern of magnetic stripes. This magnetic tape recorder was one of the key pieces of evidence that confirmed the theory of plate tectonics. In Iceland, geologists can drill into these fresh rock layers and analyze them directly, refining our understanding of Earth's magnetic history. So, Iceland is far more than a beautiful landscape. It's a dynamic classroom where the Earth itself is the teacher. It's where the formation of oceans isn't a theory in a textbook, but a tangible process you can witness. From the splitting continents at Lingvellir to the atmospheric clues released by its volcanoes, Iceland offers a unique glimpse into the powerful forces that have shaped our world and continue to do so every single day. It reminds us that our planet is not a static rock, but a living, changing entity, and we are incredibly fortunate to have a front row seat to its greatest show. Thank you for joining us on this geological journey. If you found this as fascinating as we do, be sure to like this video and subscribe for more deep dives into our amazing planet. Beneath our feet lies an ocean we cannot see, cannot touch, and until recently did not know existed. This is not a cavern filled with liquid water, nor an underground sea waiting to be discovered by some intrepid explorer. This is water in a form so alien to our everyday experience that it defies intuition. Water locked within the crystal structure of minerals, existing as hydroxyl groups bonded to silicon and oxygen atoms under conditions of extraordinary heat and pressure. The discovery of this hidden reservoir began not with drilling or exploration, but with a diamond. In 2014, scientists examining a small imperfect diamond from Brazil found something trapped inside, a mineral called ringwoodite that could only have formed in the transition zone of Earth's mantle between 400 and 600 kilometers below the surface. What made this discovery revolutionary was that the ringwoodite contained approximately 1.5% water by weight. 1.5% may not sound impressive until you consider the implications. The transition zone represents roughly 7% of Earth's total volume. If even a fraction of the rock in this region contains water at concentrations similar to that diamond's inclusion, then the amount of water stored in the mantle could equal or exceed the volume of all the surface oceans combined. The Earth, it turns out, may contain several oceans worth of water hidden in its depths. This water exists in a state that would be unrecognizable to us. At the temperatures and pressures of the deep mantle between 1,000 and 1,500 degrees Celsius and pressures over 1,000,000 times atmospheric pressure at sea level, water molecules are incorporated into mineral structures in ways that give those minerals entirely different properties. These hydrous minerals, including ringwoodite, wadsleyite, and various forms of dense hydrous magnesium silicates, can hold water much like a sponge holds liquid, except the mechanism operates at the atomic level. The presence of this water profoundly affects the behavior of the mantle. Hydrous minerals have lower melting points than their anhydrous counterparts, meaning that where water is present, the mantle can begin to melt at lower temperatures. This creates magma, and that magma, being less dense than the surrounding solid rock, rises toward the surface. As it rises and pressure decreases, the water comes out of solution, making the magma even more buoyant and, when it finally erupts, explosively releasing the accumulated volatiles. This is the mechanism that drives volcanic activity at subduction zones, those places where oceanic crust descends into the mantle. The descending plate carries with it hydrated minerals from the seafloor, serpentinites formed by the interaction of seawater with oceanic crust, and water trapped in sediments. As this material descends and heats up, the water is progressively released, rising into the overlying mantle wedge where it triggers melting and feeds the volcanoes above. But the story of Earth's internal water becomes even more fascinating when we consider the planet as early history. When the Earth formed 4.5 billion years ago through the accretion of countless smaller bodies, those building blocks likely contained significant amounts of water bound in their minerals. Some of that water would have been lost during the intense heat of formation, when the planet was partially or wholly molten, but much of it would have been retained, incorporated into the minerals of the solidifying mantle. As the planet cooled and plate tectonics began, perhaps as early as 4 billion years ago, subduction would have started carrying water from the surface back down into the mantle. Simultaneously, volcanic activity would have been releasing water from the mantle to the surface. This two-way exchange has continued for billions of years, with water constantly cycling between the surface and the interior. The question that captivates geochemists is whether the mantle is gradually drying out or being replenished. Are we slowly exporting water from the deep Earth to the surface? Or is subduction returning water to the mantle as fast as volcanism releases it? The answer has profound implications for the long-term habitability of our planet. Current research suggests that the balance may have shifted over Earth's history. In the planet's youth, when it was hotter and volcanic activity more intense, degassing likely dominated, with more water moving from the mantle to the surface than was being subducted back down. This was the era of ocean formation, when the basins gradually filled. But as the planet cooled and the rate of volcanic activity decreased, the system may have approached equilibrium, with subduction and degassing roughly balanced. Some scientists propose that we may now be in a phase where subduction slightly exceeds degassing, meaning the oceans are, over hundreds of millions of years, very slowly being returned to the mantle. If this is true, then Earth's surface might eventually become drier, though the timescale for such a transformation would be measured in billions of years. The water in Earth's mantle represents more than just a scientific curiosity. The Pacific Ocean, covering more than 60 million square miles and containing more water than all other oceans combined, did not always exist. 200 million years ago, during the age of dinosaurs, the world's geography was utterly different. The continents were assembled into a single massive landmass called Pangaea, surrounded by a vast global ocean named Panthalassa. The Pacific is what remains of that ancient sea, but its floor tells a story of constant renewal, destruction, and rebirth through volcanic processes. The oldest rocks on the Pacific floor date back only about 200 million years, a mere fraction of Earth's 4.5 billion year history. This is not because the Pacific is young, but because oceanic crust has a limited lifespan. Unlike continental crust, which can persist for billions of years oceanic, crust is continuously created at mid-ocean ridges and consumed at subduction zones recycled back into the mantle in a process that takes roughly 200 million years to complete. The engine driving this recycling is volcanic activity along the East Pacific Rise and other spreading centers that crisscross the ocean floor. Here, magma wells up from the mantle, creating new crust at a rate of several centimeters per year. As this fresh crust forms, it releases water and other volatiles that were dissolved in the magma at depth. The newly formed rock is hot, fractured, and chemically reactive, allowing seawater to penetrate deep into the crust where it is heated and altered before being expelled through hydrothermal vents. These vents, discovered only in 1977, revolutionized our understanding of both ocean chemistry and the origins of life. The black smokers, so named for the dark clouds of mineral-rich water they emit, support entire ecosystems based not on sunlight but on chemical energy, derived from the interaction between hot volcanic fluids and cold seawater. Bacteria oxidize hydrogen sulfide and other chemicals in the vent fluid, forming the base of a food chain that includes giant tube worms, blind shrimp, and specialized fish found nowhere else on Earth. But beyond their biological significance, these vents represent the continuation of the process that created the oceans. Every year, An estimated 3 billion tons of water circulate through hydrothermal systems along the world's mid-ocean ridges. Most of this is recycled seawater, but a small fraction, perhaps 1 to 5%, is juvenile water released from the mantle. Over the hundreds of millions of years that the Pacific has existed, this seemingly small contribution has added a volume of water equivalent to a significant fraction of the ocean itself. The Pacific also demonstrates the other side of the water cycle, subduction. Around its perimeter, often called the Ring of Fire, oceanic crust descends into the mantle at convergent plate boundaries. The Mariana Trench, the Japan Trench, the Peru-Chile Trench, and numerous others mark the places where the Pacific Plate and smaller oceanic plates are being consumed. As these plates descend, they carry with them enormous quantities of water, both in hydrated minerals and in sediments that have accumulated on the seafloor over millions of years. The water released from these descending plates triggers volcanic activity in the overlying plate, creating the chains of explosive volcanoes that characterize the Pacific Rim. From the Aleutian Islands through Japan, the Philippines, Indonesia, and down to New Zealand, these volcanoes are fed by water-rich magmas generated by the addition of aqueous fluids to the mantle wedge above the subducting slab. The eruptions of these volcanoes can be catastrophic. Mount Pinatubo in 1991, Krakatoa in 1883, and countless others have demonstrated the explosive power unleashed when water and magma interact under pressure. Yet these same eruptions continue the cycle, returning water vapor to the atmosphere where it will eventually condense and fall as rain, refilling the ocean basins. But the Pacific holds evidence of even more dramatic volcanic events in its past. Scattered across the ocean floor are enormous volcanic structures called large igneous provinces, the remnants of super eruptions that dwarf anything in recorded human history. The Ontong Java Plateau, for example, covers an area the size of Alaska and represents the eruption of perhaps 50 million cubic kilometers of basalt, around 120 million years ago. Such events, occurring over perhaps a few million years, would have released staggering quantities of volcanic gases into the ocean and atmosphere. The water vapor alone could have temporarily raised sea levels, while the carbon dioxide would have warmed the global climate, creating greenhouse conditions that persisted for millions of years. These were periods when volcanic activity temporarily overwhelmed the planet's ability to sequester carbon and regulate temperature, leading to major extinctions and fundamental reorganizations of life on Earth. Yet, even these catastrophes played a role in maintaining the oceans. The massive outpouring of lava resurfaced large portions of the ocean floor, and the degassing released water from the mantle that might otherwise have remained locked away for billions of years. The relationship between volcanoes and water reaches perhaps its most dramatic expression when eruptions occur beneath ice sheets or glaciers. Here, the contrast between fire and ice creates explosions of extraordinary violence, events that have shaped landscapes and, in some cases, threatened to alter the climate of entire regions. Antarctica, the frozen continent, seems an unlikely place for volcanic activity. Yet beneath its miles-thick ice sheet lie dozens of volcanoes, some active, some dormant, all testaments to the fact that the Earth's internal heat respects no climate zone. Mount Erebus, the southernmost active volcano on Earth, rises above Ross Island with its summit perpetually wreathed in volcanic gases. Its lava lake, one of only a few persistent lava lakes on the planet, has been churning for decades, releasing water vapor and other gases into the frigid Antarctic air. But Erebus is merely the visible tip of a hidden volcanic landscape. Beneath the West Antarctic ice sheet, scientists have identified at least 138 volcanoes, and the actual number may be much higher. These subglacial volcanoes present a troubling question. If they were to erupt beneath miles of ice, what would happen? The answer involves a phenomenon called Jökulhlaup, an Icelandic term for glacial outburst flood, and the consequences could be catastrophic. When magma encounters ice, the ice does not simply melt. At the temperatures involved, often exceeding 1,000 degrees Celsius, the phase change from ice to water to steam occurs almost instantaneously, creating explosive pressures. If this happens beneath an ice sheet, the expanding steam can lift and fracture the ice, while meltwater accumulates in vast subglacial lakes. Eventually, this water finds a path to escape, and when it does, the resulting flood can be devastating. Iceland has experienced numerous Jökulhlaups throughout its history. In 1996, an eruption beneath the Vatnajökull ice cap melted through 600 meters of ice, creating a subglacial lake that grew for weeks before finally bursting forth. When the ice dam failed, a wall of water carrying icebergs the size of houses swept across the coastal plain, destroying bridges and roads. The peak flow rate exceeded 50,000 cubic meters per second, comparable to the combined flow of the Amazon, Mississippi, and Yangtze rivers. These floods are not mere curiosities of the modern age. Throughout Earth's history, whenever volcanic activity has occurred beneath ice sheets, similar events have followed. During the ice ages when glaciers covered much of North America and Europe, volcanic eruptions beneath the ice would have created catastrophic floods that carved channels, deposited massive boulder fields, and temporarily raised sea levels as vast quantities of frozen water were mobilized. The channeled scablands of Washington state, long a geological mystery, are now understood to be the result of repeated catastrophic floods from glacial Lake Missoula, though not directly caused by volcanic activity. However, similar landscapes have been identified in Iceland and other volcanic regions where ice and fire coexist, bearing witness to the power of Joklaups. The interaction between volcanism and ice has implications beyond immediate destruction. When volcanic ash falls on ice sheets or glaciers, it darkens the surface, reducing the albedo and causing accelerated melting. After the 2010 Age of Geological eruption, the ash-covered glaciers of southern Iceland melted faster than usual for several years, contributing additional meltwater to the rivers and affecting water resources downstream. More significantly, major volcanic eruptions that inject large quantities of sulfur dioxide into the stratosphere can cool the global climate by creating aerosols that reflect sunlight. If such cooling were to occur during a period of marginal climate conditions, it could potentially trigger or prolong glaciation. Conversely, the carbon dioxide released by volcanic activity, particularly during periods of intense volcanism like the formation of large igneous provinces, can warm the climate and accelerate ice melting. This interplay between volcanism, ice, and climate represents a feedback system that has operated throughout Earth's history. During Snowball Earth episodes, when the planet was almost entirely frozen, volcanic activity continued beneath the ice, gradually building up atmospheric carbon dioxide until greenhouse warming eventually broke the planet out of its frozen state. The oceans that had been locked away as ice were liberated, and the water cycle resumed. In our current era, as human-induced climate change causes ice sheets to retreat, we face the possibility that volcanic systems previously insulated by thick ice may become more active. The removal of ice reduces the pressure on the crust beneath, potentially triggering increased volcanic activity. In Iceland, scientists have documented a correlation between deglaciation and volcanic eruption rates, suggesting that as glaciers melt, the frequency of eruptions increases. This phenomenon raises questions about Antarctica and Greenland. As these ice sheets thin and retreat, will the volcanoes beneath them awaken? And if they do, will the interaction between rising magma and vast quantities of ice create events we are unprepared to witness? While volcanoes created the oceans by releasing water from Earth's interior, they also played an essential role in building the continents themselves, those islands of ancient rock that rise above the waves. The story of continental formation is inseparable from volcanic activity, and understanding this connection reveals how intimately linked are the land beneath our feet and the seas that surround it. Continental crust differs fundamentally from oceanic crust. Where oceanic crust is thin, dense, and composed primarily of basalt, continental crust is thick, buoyant, and composed of rocks rich in silica, granites, granodiorites, and their metamorphosed equivalents. This difference is not accidental, but reflects billions of years of volcanic processing, a kind of planetary distillation that has concentrated certain elements at the surface, while returning others to the depths. The process begins at subduction zones, those places where oceanic crust descends into the mantle. As the descending slab releases water, that water triggers melting in the overlying mantle wedge, creating magma that is more silica-rich than the basalts of mid-ocean ridges. This magma rises through the overlying crust, where it may erupt explosively at volcanic arcs like the Andes or the Cascades, or it may stall and crystallize beneath the surface, forming large bodies of granite. Over millions of years, repeated episodes of volcanic activity and Pluton emplacement thicken the crust, building it upward and outward. Erosion strips away the volcanic rocks at the surface, exposing the granites beneath, and the eroded sediments are carried to the sea where they accumulate on continental shelves. Eventually, these sediments may themselves be caught up in collisions between continents, metamorphosed by heat and pressure, and added to the growing continental mass. This process, called crustal differentiation, has been operating since the early Earth. The oldest continental rocks, found in Western Australia, Greenland, and Canada, date back 4 billion years, to a time when the planet was still young and volcanism far more intense than today. These ancient fragments, called cratons, represent the nuclei around which modern continents have assembled through billions of years of volcanic arc accretion, continental collision, and magmatic addition. The water released by volcanoes at these ancient subduction zones did more than just fill the ocean basins. It also altered the composition of the continental crust itself, making it more silica-rich and therefore more buoyant, less likely to be subducted and recycled. In this way, volcanic degassing and crustal differentiation work together, creating stable continental platforms that could persist for billions of years while the oceanic crust around them was constantly renewed. But the creation of continents through volcanic processes had another, perhaps even more significant consequence. It created environments where life could eventually emerge and flourish. The shallow seas surrounding the growing continents provided protected environments where complex chemistry could occur. Volcanic vents, both on land and beneath the sea, supplied energy and chemical raw materials. The cycling of water between the oceans, atmosphere, and continents through evaporation, precipitation, and river flow created gradients and interfaces where different chemical regimes met. Some scientists propose that life itself may have originated at hydrothermal vents, where the chemical energy released by the interaction between volcanic fluids and seawater provided the power needed to drive the first metabolic reactions. The discovery of thriving ecosystems at modern black smokers lends credence to this hypothesis, demonstrating that life can exist and even flourish in environments we once thought utterly hostile. Whether or not life originated at volcanic vents, there is no question that volcanism created the conditions necessary for life to spread and diversify. The nutrients released by weathering of volcanic rocks fertilized the early oceans. The gases released by eruptions, particularly carbon dioxide, provided the raw material for photosynthesis, once life invented that remarkable process. And the land created by volcanic activity eventually provided new habitats for organisms to colonize, driving evolution in directions it could never have taken in an ocean-covered world. The relationship between volcanism and the biosphere has not always been benign. Major volcanic events have caused mass extinctions, poisoned atmospheres, and disrupted climate. The Permian-Triassic extinction, the worst mass extinction in Earth's history, which eliminated over 90% of marine species and 70% of terrestrial vertebrate species, is linked to the eruption of the Siberian Traps, a large igneous province that released staggering quantities of volcanic gases over a period of perhaps 1 million years. Yet even this catastrophe, devastating as it was, ultimately set the stage for the recovery and diversification of life in the Triassic period. The volcanic rocks weathered, releasing nutrients into the oceans and soil. The climate eventually restabilized. And from the survivors emerged new forms, including eventually the dinosaurs and, much later, ourselves. This paradox lies at the heart of volcanism's role in Earth's history. The same processes that create and sustain the conditions for life can also threaten it. The story of how volcanoes created the oceans is not finished. Even now, as you read these words, the process continues in the lightless depths of the sea and in the glowing vents of active volcanoes around the world. But what does the future hold? Will the oceans remain as they are, or are we witnessing the beginning of profound changes that will reshape the face of our planet over the coming millions of years? To answer this question, we must first understand that Earth is gradually cooling. The heat that drives plate tectonics, that powers volcanoes, that maintains the geodynamo generating our protective magnetic field, is slowly dissipating into space. 4.5 billion years ago, when the planet formed, it was far hotter than today, with more vigorous convection in the mantle and more intense volcanic activity at the surface. The Earth of the distant past was a more dynamic, more violent place, and the trend is toward decreasing activity. This cooling has profound implications for the water cycle. As the mantle cools, the rate of volcanic degassing decreases. Fewer volcanoes erupt, and those that do release smaller quantities of gases. Meanwhile, subduction continues, carrying hydrated minerals and water-saturated sediments back into the mantle. If these trends persist, eventually more water will be subducted than is released by volcanic activity, and the oceans will slowly diminish. Some models suggest that this process is already underway. The oceans may have reached their maximum volume hundreds of millions of years ago, and are now very gradually beginning to shrink. Over the next billion years, Earth might lose a significant fraction of its surface water, with profound consequences for climate and habitability. But other factors complicate this picture. The sun is gradually brightening, increasing in luminosity by about 1% every 100 million years. This additional energy will warm the Earth, increasing evaporation and potentially accelerating the loss of water to space. Water vapor high in the atmosphere can be split apart by ultraviolet radiation, with the light hydrogen escaping to space while the oxygen remains behind. Venus, Earth's sister planet, may have lost its oceans through this process, ending up with a thick carbon dioxide atmosphere and surface temperatures hot enough to melt lead. Earth's fate need not mirror Venus's, at least not for another billion years or more. Our planet's magnetic field, generated by convection in the liquid iron outer core, shields the atmosphere from the solar wind that might otherwise strip it away. And the carbonate-silicate cycle, a planetary thermostat involving the weathering of rocks and the burial of carbon in the ocean floor, helps regulate atmospheric carbon dioxide and therefore temperature. Volcanoes play a crucial role in this cycle. When silicate rocks weather in the presence of carbon dioxide and water, they form carbonates that are eventually carried to the ocean floor. There they are subducted and heated, releasing carbon dioxide that returns to the atmosphere through volcanic eruptions. This cycle operates over millions of years, stabilizing Earth's climate and maintaining conditions suitable for liquid water. But as volcanic activity declines, this thermostat becomes less effective. Eventually, perhaps in 500 million to a billion years, the system may fail, leading to either a runaway greenhouse as on Venus or a frozen world as the carbonate-silicate cycle grinds to a halt. There is another possibility, more speculative but worth considering. Some geophysicists propose that Earth's heat flow is not declining smoothly, but may be punctuated by periods of increased activity, when large volumes of cold material accumulated in the lower mantle finally become unstable and sink, triggering compensating upwellings of hot material. Such events might drive pulses of intense volcanism that temporarily reverse the trend toward declining activity. Evidence for such pulses may exist in the geological record. The formation of large igneous provinces, those massive volcanic events that have occurred sporadically throughout Earth's history, might represent the surface expression of these deeper rearrangements in the mantle. If so, then future supervolcanic events remain possible, even likely over timescales of tens of millions of years. What would such an event mean for the oceans? In the short term, massive degassing could add water to the surface, temporarily raising sea levels and injecting enormous quantities of greenhouse gases into the atmosphere. The climate would warm, perhaps dramatically, and ocean chemistry would shift as dissolved gases altered the pH and oxygen content of seawater. Life would face severe stresses, and extinctions would likely follow. But over longer timescales, the added water and the eventual weathering of freshly erupted rock would restore balance. The oceans would remain, their boundaries perhaps shifted, but their fundamental nature unchanged. The cycle would continue as it has for billions of years. Human activity introduces a new variable into this ancient equation. By burning fossil fuels, we are releasing carbon that was locked away in rocks over hundreds of millions of years, effectively short-circuiting the carbonate-silicate cycle. The resulting warming may alter ocean circulation, increase evaporation, and shift precipitation patterns. Ever looked out at the vast, deep blue ocean and wondered, where did all this water actually come from? It covers more than 70% of our planet's surface, a truly mind-boggling amount. The story of our oceans is an epic tale that starts billions of years ago, way back when Earth was just a baby planet. It's a story of fire, ice, and a cosmic delivery service. So grab your imaginary scuba gear because we're about to take a deep dive into the origins of Earth's magnificent oceans. Let's rewind the clock about 4.6 billion years. The solar system is a chaotic construction zone. Dust and gas are clumping together, forming planets. Earth, in its earliest form, was a scorching hot, molten ball of rock. Seriously, it was so hot that any water on its surface would have instantly boiled away and escaped into space. The surface was a hellscape of volcanic eruptions and magma oceans. Not exactly a beach-friendly destination. So, if Earth was born hot and dry, how did we end up with the world's largest swimming pool? The answer lies in two main theories, and they probably both played a part. Let's call them from the inside out and from outer space. First up, the inside out theory. As the molten Earth started to cool down over millions of years, a crust began to form on the surface. But underneath that crust, it was still a bubbling cauldron of molten rock or magma. This magma was full of trapped gases, including a huge amount of water vapor, essentially steam. Think of it like a giant planetary pressure cooker. Volcanoes were erupting everywhere, spewing these gases out into the primitive atmosphere. This process is called volcanic outgassing. For millions upon millions of years, volcanoes acted like giant chimneys, relentlessly pumping water vapor, carbon dioxide, nitrogen, and other gases into the sky. So now we have an atmosphere thick with water vapor. What happens next? As the planet continued to cool, it eventually reached a tipping point. The temperature dropped low enough for all that water vapor in the atmosphere to condense. It's the same thing that happens when you see your breath on a cold day, or when water droplets form on the outside of a cold glass. But on a planetary scale, this condensation formed massive, thick clouds that shrouded the entire planet. And then the rain began. But this wasn't just a spring shower. This was a torrential downpour that lasted for centuries, maybe even millennia. Imagine a global rainstorm that never stopped for thousands of years. This epic deluge filled up the low-lying areas of Earth's newly formed crust, the basins and craters. Drop by drop, puddle by puddle, lake by lake, these basins slowly filled, merging together to form the very first oceans. It's an incredible image, isn't it? A world born of fire, being quenched by an endless rain, giving birth to the oceans that would one day host life. But that's only half the story. While volcanoes were doing their thing from the inside, Earth was also getting some special deliveries from outer space. This brings us to our second theory. From outer space, the early solar system was like a cosmic pinball machine, with asteroids and comets flying around and frequently smashing into the young planets. For a long time, scientists have suspected that these cosmic travelers were a major source of Earth's water. Let's talk about comets first. Comets are often called dirty snowballs. They're big chunks of ice, rock, and frozen gases left over from the formation of the solar system. It makes sense, right? If you need water, why not get it from giant flying icebergs? So the idea was that a constant bombardment of comets during a period called the Late Heavy Bombardment, about 4 billion years ago, could have delivered a significant portion of the water we see in our oceans today. Each impact would have vaporized the ice, adding more water vapor to the atmosphere, which would then rain back down. However, there's a slight complication with the comet theory. When scientists analyzed the water from several comets, they found it was a bit different from our ocean water. Water is made of hydrogen and oxygen, H2O, but hydrogen has a heavier version, called deuterium. The water in comets often has a higher ratio of deuterium to regular hydrogen than the water in our oceans. It's like they're made with a slightly different recipe. So while comets definitely contributed some water, they probably weren't the main source. This is where asteroids come into the picture. You might think of asteroids as just dry, dead rocks, but that's not always true. A certain type of asteroid, called a carbonaceous chondrite, actually contains a surprising amount of water locked within its mineral structure. These asteroids formed in the outer asteroid belt, far enough from the sun for water ice to be stable. And here's the exciting part. When scientists analyzed the water from these meteorites, which are pieces of asteroids that have landed on Earth, they found its chemical signature that hydrogen-deuterium ratio is a near-perfect match for our ocean water. Bingo! This suggests that a barrage of water-rich asteroids crashing into the early Earth was a major, if not the primary source of our planet's water. It's like the universe was sending us the ingredients for life, delivered by Cosmic Express. These asteroids not only brought water, but also organic molecules, the building blocks of life itself. So, which theory is correct? The inside out or the outside in? The most likely answer is both. It wasn't an either-or situation. Earth's oceans are likely the product of a powerful partnership. Volcanoes on the young Earth pumped massive amounts of water vapor into the atmosphere from the planet's interior. At the same time, a relentless bombardment of water-bearing asteroids and comets added even more water from space. These two sources combined to fill our oceans over hundreds of millions of years. Think about that for a moment. The water you drink, the water in the oceans, the rain that falls from the sky, A significant portion of it is ancient. It was forged inside our planet and also traveled across the solar system for millions of years before arriving here. You are literally interacting with a piece of cosmic and planetary history every single day. And here's a final thought. Earth is in what we call the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist on its surface. This unique position, combined with our planet's size and atmosphere, allowed it to hold on to the water it received. Mars was likely once wet, but it lost its atmosphere and its water froze or escaped into space. Venus got too hot and its oceans boiled away. Earth was just right. The story of our oceans is a reminder of how special and perhaps how rare our blue planet is. From a fiery ball of rock to a world teeming with life, water was the key ingredient that made it all possible. It's a story written in the rocks, in the atmosphere, and in the very water we depend on. So next time you're at the beach, take a moment to appreciate the incredible journey that water took to get there. It's a journey that spans billions of years and millions of miles. Thank you so much for joining me on this deep dive into the past. I hope you found it as fascinating as I do. If you enjoyed this video and want to explore more amazing science stories, be sure to hit that like button and subscribe to the channel. Let me know in the comments what cosmic mystery you'd like us to explore next. Thanks for watching, and I'll see you in the next one.